Welcome to BKW Physics. I'm Mr. McConnelly. We're going to do parallel circuits today. Now, in a previous video, we were talking about that there's AC and DC electricity. And in high school physics, we spend most of our time with DC, direct current electricity. And we also set up the rules that govern series circuits. Now today, we're going to move over to the parallel side. And if you are not sure what a parallel circuit looks like, I've drawn an example of one that we're going to solve in a minute. And a parallel circuit means the electricity leaves, and when it gets to a point in the circuit, it has a choice of whether to go through one resistor or continue on to another. So these are parallel resistors. That's why they call it parallel. So how do the rules go? If you're wishing to find the total resistance of a parallel circuit, in a series circuit, you added them up. Well, in a parallel circuit, you do kind of a similar thing, except this time, you're adding up fractions. You're adding up the fractions. So, the 1 over the total resistance is equal to 1 over the R1, 1 over the R2, plus 1 over the R3, etc. You can go as many as you want. That is not the same. For you, for those of you who struggle with math, this is not the same as this. This is fractional, and at the end you're going to have to do an inverse. It's a very different outcome. It gives you a very different answer when you solve it mathematically. Total current. Total current, they are all equal in series. However, in parallel, you have to add them all up. So in other words, if I knew the current here, here, and here, I could add it up, and it would give me the total current that I have over here. So that's a sum of all the individual currents. And finally, total voltage. Total voltage, when you were talking in series, you added them up. When you're talking in parallel, the total voltage is the same no matter where you check it. And Ohm's law still applies, so you can draw that over also. So if I know the voltage right here, I know it at all three locations. Because whatever voltage you have coming in to the first intersection, that will apply to each of the branches. These are called branches. These are lines. Line is where all the electricity goes. A branch is where part of it goes. Now, let's do the example which will help clarify how one of these parallel circuits work. So, I've given you a parallel circuit with a battery, 3 resistors, and an ammeter right down here. And this ammeter is on this branch of the circuit. It's on this branch here. So, this ammeter is saying that anything on that yellow highlighted, if you can see the yellow, anything on this yellow part has a current of 4 amps. Okay. So I'm going to fill that in. I actually put all the variables down here. And I know that this is 4 amps. I also know that this is 5 ohms, this is 15 ohms, and this is 30 ohms. Those were givens. And my advice to you is to first find the total resistance of the circuit. So I'm going to erase some stuff so I have a little bit more room. I'm going to leave the green equations so I can refer to them. And if I want to find the total resistance of a parallel circuit, I need to use my new equation. And I'm going to need some people with calculators to follow along here. So my numbers go something like this. 1 over 5 ohms plus 1 over 15 ohms plus 1 over 30 ohms. Now, maybe the best way to do is get a common denominator. Or you can just do it out on your calculator, but that would be 6/30ths, it would be 2/30ths, and 1/30th, or 9/30ths, right? But that's equal to 1 over R total. It's not equal to R total. So if I want to know what R total is, I have to flip or take the inverse. So R total is 30 over 9, which I really need a number now. What is the answer there? 3.3 repeating? That seems about right. So now I know that the total resistance is 3.3 ohms. And you'll notice this is not a mistake. The total resistance is less than the individual resistors. And you're like, how can that possibly be? Well, it's because this. When the electricity comes over here, it has a choice of going three ways. It's kind of like if you have three parallel highways. Here near where we live, we have Route 20, Route 7, and I-88, and they all run parallel to each other. So some cars can go on Route 20, some can go on 7, and some can go on I-88. And what that does is it lessens the resistance, or it lessens the traffic. So the total resistance in a parallel circuit is less because the electrons have a choice of which road, if you want to think of it as a road, which road they want to take. So this is right. We didn't make a mistake. Well, the next thing we can do here is, since we have R3 and we have I3, can we find V3? But of course. We can use Ohm's law. Ohm's law says V3 would equal I3 times R3. So it would be 4 amps times 30 ohms. 4 times 30 gives me 120. So I know now that the voltage right here at this location is 120 volts. Now where do I go with it from here? Well, I also know, because of this rule right here, check out this rule, that in a parallel part of a circuit, all the voltages are the same. So if I know this is 120, I know this is 120, and I know this is 120, and I know the total is 120. Hey, I'm done with those. Okay, they're all equal. And then, let me just finish this and I'll get to your question, okay? And then the last thing is, how do I find these currents? Well, all I got to do here, for instance, I total would be V total over R total. So 120 volts over 3.3 ohms. Or if I was looking to find, and someone can do that on their calculator, or I'm looking to find I1, that would be V1 over R1. Or in other words, 120 volts over 5 ohms. And finally, I2 would be V2 over R2, so it would be 120 over 15. So is anyone following along with some calculator work here? We have this one?
36.36.
36.36 amps.
24.
I1 is 24?
Yep. 8.
Now let's do a little quick check here. We have learned from this law right here that all the currents should add up to the total. So let's do a back check. Does 8, 4, and 24 add up to 36-ish? Yeah, I mean we're off a little bit. That's probably a rounding error. But since these add up to that, I think we did it right. I think we're good. And this is parallel circuits physics.